Hello, welcome all. This is Prasad KVRH, welcoming you to Earth Sciences Learn It How YouTube channel. Uh, Today I am going to give a lecture on elastic theory in seismic prospecting. In this lecture, I am going to uh, explain what is elasticity and what is stress, what is strain, or what are elastic constants, what actually the relation between the three elastic constants, and later on Poisson's ratio and some important points. Okay, let's start the lecture here. Elasticity. What actually it is? Whenever we applied some external force on a material, and it will definitely undergo some deformations, either in say shape or size or length or breadth, anything. But if we remove the external force on the particular material, if it regains its original position, then it will known as the elasticity, and the particular material is called as elastic material. Here look at this spring. We are applying force in this direction, and but it is regaining its original position, and there is no change, and the no deformation is not uh, not permanent. It is regaining its original position back. That is called as the elasticity, and that material, this is known as the elastic material. Apart from elastic, there are inelastic and plastic materials also, but those type of elastic and inelastic materials are not required for seismic prospect. Perfectly elastic body is known as when it completely regains its original position and retains the same size, shape, and volume after removing of the external force also is known as perfectly elastic. Uh, all the rocks in the subsurface are assumed to be perfectly elastic in nature in seismic prospecting because the deformations are very, very, very less and small. And if we are if we are doing a near surface survey, seismic survey, when we explode something to the surface, the explosion will cause severe damage to the near surroundings. We don't measure, we don't consider those near surface seismic sources. And later on, to explain the relationships, to explain how this particular rocks or particular materials are changing their shapes and size, what are the relationship between the applied force and the corresponding changes in that material or in the subsurface. These things can be explained with the two terms stress and strain and the relationship between them, which is explained by the Hooke's law. First of all, what is stress? It is nothing but a pressure or force that we are applying on a particular material. The force per unit area is known as stress. The force will be in newtons, and the cross-sectional area or the area that is the that is getting affected by the force is known as the stress. It has SI units of Newton per meter square. The stress are two types, basically normal and shear. If the force is perpendicular to the plane of the medium or plane of the material that is affected by the stress is known as the normal stress or pressure stress. If the force applied on a material in tangential, or that is known as the shear or tangential stress. Strain is nothing but uh, strain is nothing but the corresponding changes in the shape and dimensions that because of application of this stress. Here, how the force that we are applying in normal direction or in shear direction, and it is showing the corresponding changes in the shape and size and the elongation in uh, particular area. In this normal case, the shear or that means the change in the volume or shape is perpendicular to the applied force, but in this direction There is some part is elongation or some part in the change is also in the same direction. When it comes to the types of strain, there are we can categorize into three basically: normal, shear, and volumetric. But on the basis of direction of the force, also there are two types of strain. They are longitudinal and lateral strain. If the loading or the force that we are applying in the same direction, the elongation is or the length change in the length is going to take place, then it is nothing but longitudinal strain. If the strain that is going to be takes place in the perpendicular direction in to the applied stress, that is known as the lateral strain. Or in normal strain type of strains, that is one of the norm. What is the one of the strain? This is basically due to the normal stress. Normal stress may be of two types. That is actually long compressive and tensile. When the cross-sectional area is compressed, that means the change in the length will be decreasing from original, but the cross-sectional area will be increasing. That is compressive strain. In the opposite, the tensile strain will increase the length, and at the same time it will decrease the cross-sectional area of the body. Shear. Shear is nothing but when we apply some shear stresses, then the direct in the angle of the direction there will be shear strain can be observed. Here you can observe this. This is the actual length, and this is the change in the length. The ratio between the change in the length and the original length is nothing but the shear strain. Here it can give the tan angle of the tan angle between these two. That means delta L by L tan theta. The change in the original volume, the change in the fractional of change in the volume to the original volume is known as the volumetric strain. Let's comes to the analysis of this strain. We have discussed about normal stress, normal strain, shear stress, shear strain. But actually, how they are denoted and how they have been exercised, what are the different types of normal stresses, normal strains, notations. Here we are going to discuss about. Let us see. If we consider a body of PQRS with dimensions like this is x-axis, this is y-axis. This is simply a two-dimensional body. If we applied force in this x direction and this y direction, in the x direction, if we applied the force, the corresponding change is du by dx. This is if we applying in the x direction, the corresponding change is also in the x direction. That is nothing but a normal stress. That is normal stress, and this is normal strain du by dx. And similarly in the x direction also, if we are applying in the y direction, the corresponding change is also in the y direction. Then it is the normal stress, normal strain in the y direction dv by dy. But when we applied the shear in the with the angle, so with some angle in the y direction, that will be takes place like this: du by dy, dv by dx. This combination of du by dy plus dv by dx is nothing but shear strain. The corresponding changes in the angle that causes the rotation of this particular body, the change in the angle, the change that is known as the shear strain. And there is one more thing has to be noticed here. When we consider the z-axis also, this angle this theta 1, theta 2, delta 1, delta 2, if we consider a z-axis here also, the quantity dv by dx minus du by dy by 2 will explain how much of rotation that has been takes place in the direction. If we applied the force in the x and y directions, that is nothing but rotation, but that is not a strain. All all these things are explained here. Just have a look at this. The quantity is dv by dx, du by dx, and dv by dy are the relative changes in the length along x and y directions, respectively. These are said to be the normal stresses, and that means when the normal stresses are applied, the normal strains are generated, and this is normal strain. This is normal strain, and the quantity dv by dx du by dy results in the change in the right angle in the xy plane. When the stresses are applied, it is measure of the change in the shape of the medium and known as the shearing strain and denoted by epsilon xy, and this is being denoted by epsilon xx or epsilon yy. Quantity dv by dx minus du by dy by 2 represents the rotation. As I mentioned earlier, this is not a strain. This is only rotation that is denoted by theta z in that z direction. If we consider the three-dimensional body, but here we consider only two-dimensional plane xy. If we consider three-dimensional, the corresponding normal stresses are sigma xx, sigma yy, sigma zz. Corresponding strains are epsilon xx, epsilon yy, epsilon zz, and the shearing strains are also similar to epsilon xy, epsilon yz, epsilon zx. These all are symmetric, and these are equal to epsilon yxy, epsilon yz, epsilon zx. And the rotation in the x direction, y direction, and z direction is given here like this. Here comes the important part of it: dilatation. Dilatation is nothing but change of volume to initial volume. Fractional change of volume to the original volume is nothing but the dilatation. The dilatation is a fractional change in volume of an element in the limit when the surface area decreases to zero. If delta y, delta z, and delta x are undeformed sides of an element, let it go displacements of du by dx, dv by dy, and dw by dz of the fractional changes in the volume, and that I will explain like this. And the total, the combination and the sum of this is nothing but the uh, normal strains sigma x, epsilon xx, epsilon yy, epsilon zz. And there comes the Hooke's law. We all know about Hooke's law. Under the elastic limit, the stress is directly proportional to strain that producing it. uh, Here, these are the empirical relationship between the stresses and strains, where lambda and mu are the lamb constants. After this lamb constant, we are going to discuss all the elastic constants and how they can be expressed in lamb parameters. The basic elastic constants are three. They are elastic modulus of Young's modulus, rigidity modulus or shear modulus, bulk modulus, and Poisson's ratio. These are the three constants that explain the properties and the changes and the effects that will take place when we applied the force to that particular materials. Let us discuss about Young's modulus first. It is nothing but normal stress to the normal strain. There is a proportionality constant Young's modulus of normal stress to the normal strain. The directly proportionality constant is explained as Young's modulus. It is a stress to the strain relation. And rigidity modulus is shear stress to the shear strain. It is also have the same units as Young's modulus. Bulk modulus is nothing but the pressure to the dilatation ratio. Then we are applying hydrostatic pressure, the corresponding change or the dilatation that will be explained by the bulk modulus. And the opposite, that means the inverse of bulk modulus is nothing but compressibility. And Poisson's ratio is the in the direction of the stretching force, how the longitudinal strain is changing with respect to lateral strain. This is the ratio of strains which don't have their units. That's why Poisson's ratio also don't have units. But these theoretical values are lies between 0 to 0.5. We'll discuss it later. Let us let us go for the relationship. Relation of elastic parameters in terms of Lamb constants. We'll discuss bulk modulus in terms of Lamb parameters, elastic Young's modulus in terms of Lamb parameters, and shear modulus in terms of Lamb parameters. First of all, the bulk modulus. Under normal stresses, Hooke's law explains sigma xx equals lambda d plus 2 mu epsilon xx. Here, sorry for the mistake, I have to write here yy and zz here. If we add all these three, it will give like this. And this is nothing but dilatation. We have discussed it earlier. Under hydrostatic pressure, the normal stresses are equal to pressure and the negative symbol to make it as positive, because in the opposite direction that we are applying it to the normally. And if we substitute these two values in this, we will get minus 3p equal to 3 lambda delta plus 2 mu delta. And if we make some changes and if we substitute this p in the definition of bulk modulus, that is nothing but pressure to the dilatation, then it will gives k equals lambda plus 2 by 3 mu. This is the relationship between bulk modulus and shear modulus and lamp parameter. The Young's modulus describes in the longitudinal strains. When we are considering uniaxial stress, only longitudinal stress is applied. Then the y and z direction, there is no stresses because we are considering uniaxial stresses. Then if we add these three together, we will get these results like this. On substituting the value in the Hooke's law of, because we are considering in the x direction only, that's then it will becomes like this is stress component, and this is the strain component. We have to make all the stress components in the same side and we will get the relationship between stress and strain. These are normal stresses. We have a relationship between normal stresses, that is nothing but Young's modulus explained as this mu into 3 lambda plus 2 mu by lambda plus mu. This is the relationship between elastic Young's moduli and lamp parameters. And then followed by the shear modulus. By the definition, it is shear stress to the shear strain. Simply force per unit area to the corresponding change in this after applying of the shear stress. For smaller angle of pi, we know that tan phi will equals always phi, and the numerator we know that force per unit area is nothing but the change in the pressure. Then the whole stress and strain relationship will becomes like this. First, let us discuss, just like in for the sake of understanding, let us consider a rectangular prism undergo shear deformation in xy plane. The total extension is given by dx by x equals dp by e into 1 plus nu. Don't bother about where this nu comes from. It is not, it is where this nu comes from. This nu is coming from the definition of shear modulus. For small deformation of neglecting higher order terms in the diagonal extension, it will be the dt by 2 dt by d equals to pi by 2. If we equals this 2, if we equals this 2, we will get the relationship between e and nu and mu. Then it will becomes e mu equals e by 2 plus 1 into nu. Let us express the Poisson's ratio in terms of lamp parameters. We know shear modulus, we know Young's modulus. We have to substitute those two values to get the Poisson's ratio here, and then the Poisson's relation explained as lambda by 2 into lambda plus mu. So, what are the important notes we note down here? Elastic constants will be defined in such a way they are to be positive. We are defining the elastic constants in such a way that are to be positive. And E, K, and mu elastic Young's modulus, bulk modulus, and shear modulus lies in the range of 10 to 200 gigapascals. For the most of the rocks, this range is enough, but there are some other rocks with the extreme values also. We will discuss it later uh, in the seismic exploration parts. Among the three elastic modulus, Young's modulus will be the largest, while the shear modulus will be the smallest. Poisson's ratio theoretically lies between 0 to 0.5. For very hard rocks, the Poisson's ratio will be 0.05, while for the very very poorly consolidated material with high porous and permeability nature, that will be 0.45, and zero point 0.5 for completely shear resistant, not shear doesn't have shear resistant bodies, they will have the zero point 0.5 as Poisson's ratio. Example, outer core, it doesn't have shear resistance, that's why it has shear modulus as 0 and Poisson's ratio as 0.5. That's why shear waves doesn't travel in outer core, because of it has no shear resistance. The values of lambda and mu are almost equal in some materials. Some materials which have Poisson's ratio as 0.25, such materials are known as Poisson's solids. That's it from my side. Please mention your comments, questions, queries, suggestions, and critics. All are welcome here. And in the next lecture, I'm going to discuss about anisotropy. So please follow, please share, please subscribe, and please try to learn something new. Yeah, that's it. Thank you.